So I want to start today with a bit of a thought experiment. It's actually a frustration I think we've all felt at some point, specifically when we're reading.
Okay, I'm intrigued. What kind of frustration?
Well, imagine you are trying to read a regular sentence in a book, right? But I've taken a blank piece of paper and I've cut this tiny, narrow vertical slit right in the middle of it.
Like a little window.
Exactly, a little window. And you have to slide this slit across the text, moving strictly from left to right.
So I'm just scrolling across the line,
Right.
basically. I can see the exact word I'm currently looking at through the window. And I guess, maybe I have a vague memory of the words I just passed on the left.
Right, you remember the past, but
Yeah.
everything to the right of that slit, it is just pitch black. You have absolutely no idea what is coming next.
You're completely blind to the future of the sentence.
Completely
I
blind.
mean, that sounds like a nightmare, honestly. You would lose all sense of nuance. You wouldn't even know if the sentence was a question until you physically hit the question mark at the very end.
Right, and the ambiguity is the real killer there. Like, think about this. If you see the phrase, the man went to the, and the next word is blocked out by the paper, you are totally paralyzed.
Oh, because of words with multiple meanings.
Yeah, exactly. Did he go to the bank to deposit a check, or did he go to the bank to, like, sit by the river and fish?
You wouldn't know.
You wouldn't. Without seeing that future context, the word fish or the word deposit later in the sentence, you cannot effectively process the past context.
You're just flying blind. And, to bring this right back to our world, for a really long time, that exact slit in the paper method was exactly how computers processed human language.
Stuck reading in one single direction.
Yeah, they were stuck. Until the paper we are doing our deep dive on today completely changed the rules.
It really did. And welcome, everyone, to today's deep dive. We are unpacking an absolute heavyweight today.
A total game changer.
We are looking at the 2018 landmark paper. It's called BERT, Pre-Training of Deep Bidirectional Transformers for Language Understanding. This comes from Jacob Devlin and his colleagues over at Google AI Language.
And if you've been following our series here on the foundations of generative AI, this is a massive pivot point.
Oh, it's huge.
It really is the moment where natural language processing, or NLP, stopped just guessing what word came next and actually started understanding the whole picture.
So our mission today is to look at how BERT just smashed the state-of-the-art records on 11 different language tasks effectively overnight.
And how it beat human experts at reading comprehension, which is still crazy to think about.
Yeah, we're going to figure out how it did all of this by essentially playing a really high-speed game of fill in the blank.
It is such a deceptively simple concept, but it required this massive shift in how he engineered these models.
So let's set the stage a bit. The year is 2018. What did the world of AI look like before BERT showed up?
Well, we mentioned that slit in the paper analogy. So the dominant architecture at the time was the recurrent neural network, the RNN.
Right.
And specifically, we were just starting to see the rise of the transformer architecture. But, and this is the critical key here, models like the original OpenAI GPT, they were autoregressive.
Autoregressive. That is one of those highly technical terms that gets thrown around a lot in these papers. Let's break that down for the listener.
It sounds complicated, but it simply means the model consumes text sequentially, usually just left to right.
Just reading forward.
Exactly.
Yeah.
To predict the next token, it can only attend to the tokens that came before it. It's that slit in the paper.
Yeah.
If the model is processing the word bank, it absolutely cannot see the word river 5 words later.
So it has to make this probabilistic guess based solely on history. It's trying to predict the future based only on the past without being allowed to peek ahead at all.
Exactly. And researchers, they obviously knew this was a massive limitation. They knew that true language understanding requires context from both sides of a word.
You need the left and the right.
Right. And there was a pretty notable attempt to fix this before BERT, a model called Elmo.
Elmo, yes, named after the Sesame Street character. I always love that.
Yeah, the NLP community loved their Muppet acronyms. Elmo stood for embeddings from language models.
And how did Elmo try to fix the slit in the paper problem?
Well, Elmo tried to solve the context problem by training 2 completely separate models. One model read the sentence strictly left to right. The other model read the same sentence strictly right to left.
Okay, that sounds fairly logical on paper. It's kind of like looking both ways before you cross the street. You get the full picture from both directions.
Ideally, sure. But here is the catch, and this is exactly why BERT had to be invented. Elmo just took those 2 independent results and essentially stapled them together at the very end.
Just glued them together.
Yeah, it's a process called concatenation. It wasn't a true fusion of the information. The left-to-right brain didn't know what the right-to-left brain was thinking until the very last second of processing.
So it's shallow.
Very shallow.
It's essentially two unidirectional models wearing a trench coat, pretending to be one bidirectional model.
That is a perfect way to put it. It is shallow bidirectionality. And this is exactly where BERT enters the chat and just flips the table on everyone.
Because BERT stands for bidirectional encoder representations from transformers.
Exactly. And BERT basically said, I don't want two shallow brains. I want one deep brain that looks everywhere at once.
And that is the deep bidirectionality mentioned right in the title of the paper.
Precisely. BERT uses a transformer encoder. So it looks at the entire sentence, the words before and the words after, simultaneously. And it does this in every single layer of the neural network.
It's taking it all in at once.
It's not predicting the next word sequentially at all. It's building a rich representation of the entire concept simultaneously.
But hold on, let's play devil's advocate for a second. There is a reason people didn't do this before BERT, right?
Oh, absolutely.
It's not that nobody thought of looking at the whole sentence, it's that doing so introduces a huge paradox.
It introduces a massive, massive problem for training the AI.
Right, because if the model can see the words to the right, isn't that just cheating?
That's the exact word for it, cheating.
Like if I ask you to guess the missing word in a sentence, but I leave the answer key sitting on the desk right next to you, you aren't learning English. You're just looking at the answer.
And that is the exact problem that held back bidirectional training for years. If a model can see itself in the future context, the prediction task becomes trivial.
The model just copies it.
Exactly. The loss function, which is the math that measures how wrong the model is so it can learn, well, that loss function just goes to zero immediately.
No.
The model learns absolutely nothing because it doesn't have to learn anything.
It takes the lazy route.
Always.
Yeah.
It just copies the target word from the future context.
So the researchers at Google had this really powerful engine, this deeply bidirectional transformer, but they couldn't train it the normal way.
They had to get creative.
They had to come up with a way to let the model see the whole sentence without letting it cheat.
And their solution was actually inspired by something called the close task, spelled C-L-O-Z-E, which dates all the way back to 1953.
Wow, 1953. Okay, so this brings us to what the paper calls task number 1, the masked language model, or MLM.
Right. So instead of asking the model to predict the next word, which is what GPT was doing, they take the input text and randomly hide or mask some of the words.
They just delete them.
Basically, specifically, they hide exactly 15% of the words.
Okay, so instead of feeding it a sentence like, my dog is hairy, the computer sees my dog is mask.
And because the actual word hairy is effectively erased from the input, the model has to look at the words my dog and is to figure out what fits.
It has to infer the missing piece.
But here is the magic part. Because it is a deep transformer, it can also look at the words after the mask if they exist in a longer sentence. It forces the model to use context from both directions to fill in the blank.
And it can't cheat because the answer literally isn't anywhere in the input.
Exactly. It's a brilliantly simple, intuitive leap. If seeing the word is cheating, just delete the word.
But, reading through the paper, there is really interesting nuance here that I found fascinating, because they don't actually just put a big blank mask sticker over the word every single time, do they?
No, they don't. And this is one of those brilliant little engineering details that makes BERT work so well in practice. Think about it this way. If you train an AI model where it always sees a specific mask token when it needs to make a prediction,
Right.
what happens when you try to use that model out in the real world?
Well, real sentences out in the wild don't have mask tokens floating around in them. If I'm asking the model to analyze a news article for me, the article is complete. There are no blanks.
Exactly. You get this mismatch between the training environment and the real-world application. The model might get confused because it's actively looking for a mask token that simply isn't there.
It relies too heavily on that specific artificial signal.
Yes, it overfits to the mask token.
It's kind of like training a mechanic who only knows how to fix a car engine if there's a giant neon red X painted directly on the broken part.
That's a great analogy.
If the red X is gone, they open the hood and just throw their hands up. They don't know what to do.
Exactly. So to prevent that, the Google researchers mix things up. When a word is chosen to be hidden, that 15% we talked about, they don't always use the actual mask token.
Okay, so what do they do instead?
Well, 80% of the time, yes, they use the mask token. But 10% of the time, they replace the target word with a totally random word from the dictionary.
So the sentence, my dog is Harry, might become my dog is Apple.
Right. And remember, the model does not know which word has been randomly changed. It just sees the full sentence.
That seems like it would just deeply confuse the poor model. Why lie to it like that?
Because it forces the model to not just lazily look for a mask. It forces it to actually check every single word it sees to see if it makes logical sense in the surrounding context. It effectively asks the model to look at apple and say, wait, does apple belong here? No, apple doesn't fit with dog.
So it forces the model to maintain this really robust, what did they call it in the paper? A distributional contextual representation of every single token.
Yes, it has to constantly validate reality against its understanding of language.
That is so clever. And then there is still 10% left over. So 80% mask, 10% random word. What about the final 10% of the time?
The final 10%, they just leave the original word alone. The input is just, my dog is Harry.
But it still has to predict it.
Yes. The model still has to output a prediction for that position. It has to look at the word Harry and say, yes, based on the context of my dog is, the word Harry is indeed the correct word.
Which prevents the model from getting lazy and just assuming that if a word is visible, it must automatically be right.
Exactly. It keeps the model on its toes constantly.
Okay, so that is task number 1, the masked language model. And that teaches the model about words and context within a single standalone sentence. But understanding human language is a lot more than just filling in isolated blanks. You have to understand how entire sentences flow together.
You need logic. You need inference, argumentation, basically the stuff that makes a paragraph actually readable.
Right, because if I say, the man went to the store, and the very next sentence is, penguins are flightless birds, those are both totally valid English sentences. Grammatically, they are flawless.
But they have absolutely zero relationship to each other. They're completely disjointed.
Exactly. And if you are trying to build a question answering system or maybe a summarization tool, the AI needs to know if sentence B actually follows sentence A. It needs to track the thread of the conversation.
And that brings us to the second breakthrough, task number 2, next sentence prediction, or NSP.
NSP.
The researchers realized that just learning word associations by masking wasn't enough for true comprehension. They needed to formally teach the model to understand the relationship between sentences.
So how did they train BERT to figure that out? What was the game there?
They fed BERT pairs of sentences. Let's just call them sentence A and sentence B.
Okay.
50% of the time, sentence B was the actual real next sentence from the original document. The paper labels this as is next.
Exactly.
The other 50% of the time, sentence B was just a completely random sentence pulled from somewhere else in the corpus. And they labeled this not next.
So it's a binary choice, just a simple coin flip for the model. Is this next or is this random?
It sounds simple for a human, maybe, but for a machine to do this with high accuracy, it has to essentially read the first sentence, understand the topic, the tone, the subject matter, and then analyze the second sentence to see if it logically continues that specific thought.
And how did BERT do on that?
The final model achieved between 97 and 98% accuracy on this specific task.
That is incredible. And to train it to do this, they must have needed just massive amounts of data. I mean, you couldn't just feed it a bunch of unrelated tweets or randomly shuffled sentences.
No, absolutely not. They needed contiguous text,
Right.
long passages where the natural flow of ideas is actually preserved.
Where did they get it?
They used the book's corpus, which is about 800 million words drawn from unpublished novels and books.
Wow.
And they combined that with English Wikipedia, which gave them another 2,500 million words.
So that's 3.3 billion words in total.
Yes.
And I actually noticed a really specific detail about how they used Wikipedia. The paper notes that they actively ignored all the lists and tables.
Yeah, they only wanted the prose. They wanted the flow of natural human language, not just structured data points or bulleted headers. They really wanted the model to learn the rhythm of human thought.
Okay, so let's take a breath here and just look at what we have built so far. We have this massive digital brain. It has played fill in the blank billions of times. It has played is this next billions of times. It has spent days cooking on massive hardware.
Which brings us to the overarching framework that really defines the legacy of this paper. This is arguably the ImageNet moment for text processing.
Yes, let's talk about pre-training versus fine-tuning, because this is the conceptual leap that completely changed the AI industry. Break this down for us.
For sure.
Because before BERT, If I wanted a model to analyze sentiment in, say, movie reviews, and you wanted a model to find specific legal clauses in a contract, we were essentially building two completely different houses from the ground up.
Exactly. We were building custom bespoke architectures for every custom job. You would have your special sentiment model. I would have my special named entity recognition model.
We started from scratch every single time.
We did, initializing with random weights and then tried to train on our specific, often very small, data sets. It was inefficient.
And BERT changed that by introducing what I like to call the Swiss Army knife approach.
Yes. The framework has two totally distinct stages. Stage one is pre-training. This is the heavy lifting phase.
The reading phase.
Right. This is where BERT reads Wikipedia and the books corpus for days on end. For their largest model, BERT Large, this pre-training phase took 4 full days running on 64 TPU chips.
And just quickly for the listener, TPU stands for Tensor Processing Unit.
Right. Those are Google's custom-built hardware chips specifically designed to accelerate machine learning.
So this pre-training stage is wildly expensive.
Very. It is computationally intense. It costs thousands and thousands of dollars in electricity, cooling, and hardware time.
But once that massive upfront cost is paid and the pre-training is done, you are left with this generic language genius.
You have a foundational model that understands the deep structure of English. That's stage one.
And stage two.
Stage two is fine-tuning. You take that exact same pre-trained BERT model, the one that already knows about history and science and grammar from Wikipedia, and if you want to teach it to answer medical questions, you just add one tiny little output layer on top of it.
It's just one layer.
Just one, and then you train it on your specific question and answer data set.
And the paper points out that this fine-tuning part is actually incredibly cheap.
Oh, it's remarkably cheap. We're talking about maybe 1 hour on a single cloud TPU, or maybe a few hours on a standard consumer-grade GPU.
So you do not need a massive supercomputer to fine-tune BERT for your specific job.
Not at all. You can take this massive world-class language engine that Google spent millions developing, and you can specialize it for your own specific problem with very little effort or cost.
It totally democratized high-end NLP.
It really did.
You didn't need Google's massive budget to have Google-level AI capabilities anymore. You just needed their pre-trained model as your starting point.
Precisely. It allowed transfer learning to finally work for text, in the same way it had been working for computer vision for years.
So let's talk about the results. They built this architecture, they pre-trained it on billions of words, they fine-tuned it for specific tasks. How did it actually do against the competition at the time?
It didn't just win. It completely cleared the board.
Tell us about the benchmarks.
They tested it on the GLUE benchmark. GLUE stands for General Language Understanding Evaluation. It's essentially a rigorous collection of 9 very different, very difficult language tasks.
Like what kind of tasks?
Everything from sentiment analysis to textual entailment, which is figuring out if one sentence logically proves another.
Okay, so give us a sense of the scale of BERT's victory here. Was it a close race? A photo finish?
Not even close. So the previous state-of-the-art system was the OpenAI GPT model, which had an aggregate score of 72.8%.
Okay, 72.8.
BERT base, which was the exact same physical size as GPT, meaning it had the same number of parameters, jumped all the way to 80.5%.
Wow. That is a massive leap in a field that usually fights tooth and nail for like 0.5% improvement.
Exactly. And remember, that was just the base model. They also trained a bigger version, BERT Large, which had 340 million parameters compared to the base model's 110 million.
And I'm guessing BERT Large did it even better.
BERT Large crushed everything even harder. It set new state-of-the-art scores across the board.
I actually saw some notes in the paper regarding human-level performance. Now, that is a very bold claim. Are the authors saying BERT reads better than a human being?
Well, within some very specific constrained parameters, yes. Look at their results on Squad.
That's the Stanford question answering data set, right?
Yes. The way it works is you give the AI a paragraph of Wikipedia text, and then you ask it a specific factual question about that text. BERT not only outperformed all the top systems on the leaderboard, it actually beat the metrics for expert human performance.
That is just wild. It's reading a text and finding the answer more accurately than a person. And there was another benchmark, too, SWAG.
Yes. SWAG. It stands for Situations with Adversarial Generations.
I love that,
It's
man.
a great acronym. SWAG is basically a common sense test. You are given a sentence like, he is playing the piano, and then you have to pick the most plausible next action from a multiple choice list of 4 options.
And some of those options are tricky distractors designed to fool the AI.
Exactly. But BERT beat the dataset author's own baseline model by 27%. And once again, it surpassed human expert performance levels, 86.3% for BERT versus 85.0% for humans.
I want to dig into that size matters point you made a second ago. You mentioned BERT large significantly outperformed BERT base. The paper dedicates a whole section to this called ablation studies.
Right. So an ablation study is basically where you carefully remove or alter specific parts of a neural network to see what is actually driving the performance.
It's like taking ingredients out of a recipe one by one to see if you can still taste the difference.
Exactly. If you take out the sugar and the cake tastes exactly the same, well, the sugar wasn't an important ingredient.
And one of the main things they tested in these ablation studies was model size. They tweaked the number of layers, the hidden units, the attention heads.
And this produced one of the most surprising and impactful insights of the entire paper.
Why was this surprising?
Because conventional wisdom in machine learning at the time strongly dictated that if you have a very small data set for your specific task, say only 3,000 examples to learn from, you absolutely must use a small model.
Because if you use a giant bazooka of a model on a tiny little data set, you are going to overfit.
Right, the model would just memorize the exact training data instead of actually learning the underlying patterns.
That makes intuitive sense.
That was the widely held assumption. But BERT proved that if your pre-training is good enough, if the model has deeply read enough text in that first massive unsupervised stage, then the rule of bigger is better holds true even for very small downstream tasks.
So they test this theory on a small data set.
They did. They used the MRPC task, the Microsoft Research Paraphrase Corpus. It only has 3,600 training examples. It's tiny.
And how did the big model do?
The giant BERT large model still performed noticeably better than the smaller BERT-based model. No catastrophic overfitting.
That really flips the script. It suggests that in 2018, researchers hadn't even come close to hitting the ceiling on model size yet.
We definitely hadn't. It signaled to everyone that scaling up wasn't just about giving the model more data to memorize, but about creating fundamentally better, deeper representations of language that worked everywhere, no matter the task size.
Before we wrap up, there is one more technical nugget from the paper I want to make sure we highlight. We spent a lot of time talking about fine-tuning, which involves lightly updating the whole model.
Right.
But the paper also showed that you can use BERT in a way that's much more like the older Elmo model we discussed.
Ah, yes. The feature-based approach. This is super important for listeners who might be dealing with strict computational constraints.
Right, so explain how that works. You can just freeze the BERT model, right? You don't let its internal parameters change or learn anything new at all.
Exactly. You lock it down.
Yeah.
Then you just pass your sentence through the frozen BERT model, and you extract its internal math, the deep numerical embeddings it generates for the words.
And then you feed those numbers into a totally different, much cheaper, simpler AI system.
Think of it like taking the massively powerful engine out of a Ferrari, but just hooking it up to power a go-kart. You aren't retraining the Ferrari engine, you're just extracting its raw power for your own use.
So if a developer literally cannot afford the compute power to fine-tune the whole massive network, they can just use BERT's brainwaves, so to speak.
Essentially, yes. And the paper showed it still performed incredibly competitively. Using the feature-based approach, it was only about 0.3 points behind the fully fine-tuned version on named entity recognition tasks.
That is fantastic. It offered ultimate flexibility. You didn't have to fine-tune to get the core benefits of BERT's deep understanding.
It met developers where they were.
So let's zoom out here at the end. Why does a research paper from 2018 still matter to you, listening to this deep dive today? I mean, we live in the era of GPT-4, Gemini, Claude. BERT kind of feels like ancient history in AI years.
It does. But BERT is the grandfather of all of them. BERT established the exact blueprint the entire industry follows today. Before BERT, NLP was completely fragmented. After BERT, the gold standard became crystal clear. You take a massive transformer model, you pre-train it on an obscene amount of data using self-supervised learning like the master-word task, and then you fine-tune it for whatever specific job you need.
It totally shifted the paradigm from how do I build a model from scratch for this one task to How do I adapt the foundational model for this task?
Precisely. Whether you are looking at modern massive LLMs or specific enterprise AI tools, they are all standing directly on the shoulders of BERT's deep bidirectionality. It proved you don't need painstakingly human-labeled data to learn the structure of language.
You just need raw text and a really clever way to hide the words.
Exactly.
It is honestly amazing to think that just randomly covering up 15% of a sentence completely revolutionized computer science.
Sometimes the constraints we invent are exactly what force the breakthrough. By blinding the model, we actually forced it to learn how to truly see.
That is a great way to put it. So, as we wrap up, here's a final thought for you to chew on today. This paper proved, empirically, that scaling up going from 110 million parameters to 340 million gave strict, undeniable improvements across the board.
It taught the industry that bigger is better.
And the industry definitely listened. We went from millions of parameters to billions and now to trillions.
We certainly did.
But I have to wonder, if BERT showed us in 2018 that brute forcing massive size works even for tiny little tasks, did we accidentally walk into a trap?
What kind of trap?
Well, did strictly following that bigger is always better logic lead us to a place where we are now building models that are just too computationally expensive and power-hungry to be sustainable long-term, simply because we know the brute force method works?
That is the multi-billion-dollar question right there. We are actually starting to see a swing back right now towards small language models and a renewed focus on efficiency.
Because we can't just keep building bigger data centers forever.
Exactly. BERT undoubtedly started the global race for size. But I think we are still actively figuring out if the absolute biggest model is always the smartest way to solve a problem.
Efficiency versus raw performance. It is a battle for the ages in computer science. Thank you so much for diving deep with us today. We'll see you on the next one.